D'Alembert's solution for the one-dimensional wave equation is a little highlight of this course. It is a very nice formula, and in this course we will see at least 3 methods to derive it. So here I'm going to use the method of characteristics, but then you can also use separation to get this solution, and later we will use Fourier transform to again derive D'Alembert's solution. So it is so important that we even have 3 derivations of this one formula. Curious? Let's see. So here we go. Here's the one-dimensional wave equation on an infinite domain, minus to plus infinity. And then we have 2 time derivatives, 2 spatial derivatives. Okay, so by the rule of thumb, we need 2 initial conditions, which are given here. Initial translocation f and initial velocity g. And since the domain is infinity, we do not have 2 conditions on space, because there is no space boundary. So what can we do? So we learned the method of characteristics for equations of first order, but here this is of course second order. So how can we make this into a first order equation? Ha! And the idea is actually rather cool. So instead of d square u by dt square, let's just write a square. Okay? Just use the symbol a. Let's say maybe a is d by dt, the first derivative. And if I apply it twice to u, then I call this maybe a square. Okay? And then the other side I call b square. So the c square I keep, and then maybe let's call du by dx b, d by dx. And then what I really have is something like a square minus cb square u is 0. The time derivative is called a, the spatial derivative is called b. Okay, and then I apply this kind of differential operator, a square minus c square b square, to u. But now let's forget for a moment that these are differential operators and just consider they are numbers. Because if they are numbers, I can use a binomial relation, right? A plus cb times a minus cb times u is 0, right? Because a plus cb times a minus cb is exactly a square minus c square b square. All right. So now let's replace the operators. So that this would mean d by dt plus c d by dx. Okay. If I replace the differential operators, and then d by dt minus c d by dx. U is 0. And then I have my first order problems. I have ddt plus c ddx. This is something we have solved before with the method of characteristics. ddt minus c ddx, same thing, just the c has a negative sign. We can again use the method of characteristics. This is what I wrote down in 1028, right here. And now what we do is we call this bit here, we call this to be v. We give it a new name. So this is written right there. v is d by dt minus c d by dx u. Or if we write it out, it is du by dt minus c du by dx. So we get all of a sudden 2 variables. We have u anyways, and now we have another variable v. So we in the end have to solve 2 equations. What happens at time 0? Well, at time 0 we use this formula here. So we get du by dt at 0 minus c du by dx at 0. But then these were given. The initial velocity was g, and the initial displacement is f. So then we get a derivative, so we get f prime. Okay? So this is the initial condition for v. Now let's call this thing here, let's call this f of x. Just give it a new name for now. So then if we collect all this, we get 2 equations. We get a v problem where we have like a plus c, first order differential equation, and this new f. And we get the u equation where we have a minus c, and f is the initial displacement, the initial condition. And here I wrote down capital F again, so it's g minus cf prime. But now 1029 and 1030 are simple first order PDEs where we have done method of characteristics. Okay, so now let's go and solve 1029 first and then 1030 second, because 1039 first because a v actually is used here, right? So there's a direction. We have to do 1029 first. But we can, because the solution, as we have done before, is just a shift. It is shift to the right, which is written as x minus ct of the initial condition. So then we take this v and put it into the second equation for u. So then we have a first order differential equation for u, but now the f is written as x minus ct, big F at x minus ct, and again the big F is here, g minus c f prime. To solve this, here I refer back to the general formulation of the method of characteristics, where we have a curve of anchor points. And in the easiest cases, as we have seen, the anchor points can be chosen to be at time is 0. And this is exactly the case here. So we can choose the anchor points sitting at time 0, and then the anchor point is just called A. So it's really the simplest case which we can have in this case. On the anchor point, at time 0, the value of the function will then be the initial condition, f at A. Perfect. So then we can summarize the characteristic equations right here. We have dx by dt is minus c, x0 is the anchor point, dz by dt is the fx minus ct, the right hand side, and the value at the anchor point is f of a. So the first one, dx by dt is minus c, is of course solved by minus ct plus a. Very simple thing. So then we take this minus ct plus a and plug it here. So this would have been. So there needs to be a plus. And this is the x. And then here we have plus a on this term. So there the sign is correct. So it's a little typo there. So dz by dt, second characteristic equation, is f at a minus 2ct. We integrate this over time. Integral from 0 to t. So then z is the integral from 0 to t. The right hand side, which is f of a minus 2c dx, and then we get a constant of integration. Now the constant of integration we can find from the initial condition if we set in t is 0. Okay, then we get z at 0 would be just the k. So that's the initial condition at the anchor point. So then this is f at the anchor point A. Wonderful. So then we are down to this formula here. Let's recall what f is. The big F is in fact g minus c f primes. Now here we do a substitution. So we call this to be equal to mu. Okay. And then the limit changes to a minus 2ct, from a to a minus 2ct. And the dc changes to a d mu with a minus 1 over 2c in front. So here we use the substitution. And then we replace f with g minus c f prime. This happened here. And now f prime is a prime. It's a derivative. So this is something we can integrate right away. So then we keep the 2 from the 1 over 2c, but the factor c cancels. And the 2 minus sign give a plus. And so here we get f mu evaluated between a and a minus 2ct. The g integral we leave untouched. And then for the g integral we flip the order of integration. You see here this went up and this went down, eating the minus sign. For the f we do the evaluation, so it's f at a minus 2ct minus f of a. Okay. So that's still not nice enough. I want to have a nicer formula. Here I summarize the same formula once more. Now I like to invert the transformation. So I want to replace the anchor points. And I know already the anchor point is x plus ct. So let's put that there and there and there and one more. Zip. So then here's what you get. So here we replaced all them, right? There's the anchor point. There's the anchor point minus 2ct, anchor point minus 2ct, and anchor point. So all makes sense. Perfect. And now we just need to simplify, right? So here we have a ct minus 2ct, so it's a minus ct, like here. And the same happens here at the lower end, and the upper end is the same. So what we get It's a wonderful dAlembert's formula. So the solution is a half f of x plus ct plus f of x minus ct. It's a very nice symmetric expression. F was the initial condition for u, and g was the initial velocity, so this is integrated from x minus ct to x plus ct, and then 1 over 2c. This is dAlembert's formula. We will gonna play with this formula quite a bit, and in examples you will actually see how wonderful it is and how much we can understand about the behavior of waves for the wave equation.